So for section 11.4, we're going to take a look at the inverse of a square matrix. So one way to describe a square matrix is by its order number. So a 2 by 2 matrix has 2 rows, 2 columns. That's what makes it a square matrix. And we can call that a matrix of order 2. And a square matrix that's 3 by 3, we can say it's order 3. And a matrix that's 4 by 4, we can say it's order 4. It's just a way to describe the size of that square matrix. Another thing we have to look at is what we call the multiplicative identity. And what that means is it's a matrix, first of all. So if we have a multiplicative identity of order 2, that's the matrix 1, 0, 0, 1. So what it is a 2 by 2 matrix where if I were to multiply this matrix by another matrix, as long as the operation is defined, we should get what we began with. So one way we write that is I subscript 2 is a way to use notation to describe the identity matrix of order 2. And then similarly, if we have a 3 by 3 multiplicative identity, or 3 by 3 matrix, that's an identity, we can use I subscript 3. A lot of times, just for computation convenience, the subscript is kind of omitted, not put there. But the idea there is if we have an identity matrix without the subscript, it should be the same size as the matrix we're multiplying it by, and you'll see how that works out here in a problem. So next thing we have to talk about is what does multiplicative identity have really anything to do with what we're going to be looking at today. So first thing is if we have a matrix A times a matrix B, and we get an identity matrix, so in this case, the subscript there is not written, so we have I, could be I2, I3, I4, just depends on the size of the two matrices we're multiplying. So if A and B are both square matrices, and we multiply them together and get an identity matrix, or multiply B times A, because the order of matrix multiplication does matter. If we get the identity matrix in both cases, we would say A is invertible, which means we can find an inverse, and matrix B would actually be its inverse. So the idea is if I take a matrix and multiply it by its inverse, we should get an identity matrix both directions, so A times B and B times A. Now if it's not possible to find an inverse of a matrix, we can say two things. Either it's not invertible, or the word we usually use for that is singular. Every square matrix that has an inverse has only one inverse, so the idea there is inverse matrices are unique. There's only one for each one if there is a possibility to find one. And then the notation we use for an inverse would be the same notation we use for function inverse, which is A and then to the power of -1 means we are finding the inverse or A inverse matrix. So for the first example, what we're going to do is take a look at how to multiply a matrix by an identity, just to verify how the multiplicative identity matrix works. So if I take matrix B and I want to multiply it by I, notice the subscript for I is not written, but we should know that if we're multiplying a square matrix B, which is 2 by 2, the identity matrix we're going to be multiplying is also a 2 by 2. So if I were to work through this operation here, B times I should get, row 1 times column 1, I should get a half. 1/2 times 1 plus 5 times 0. And row 1 times column 2, I should get 5. And then row 2 times column 1, I should get 3. And row 2 times column 2, I should get 1. So the idea there is if I take matrix B and multiply it by the 2 by 2, or the multiplicative identity of order 2, I should get matrix B. And that should work also reverse order. So if I take I, which is a 2 by 2 identity matrix, and multiply it by B, row 1 times column 1 should give me a half. Row 1 times column 2 should give me 5. Row 2 times column 1 should give me 3, and row 2 times column 2 should give me 1. So that just verifies how the identity matrix gives me the same matrix I began with when I multiply. So for example 2, we're going to take a look at how to compute the inverse of a matrix. So essentially the process is going to be, we're going to take a matrix and augment it with the identity matrix of the same size. And when we do that, we're going to try and use row operations to get the left side of the dashed line to become an identity matrix and what I get on the right side should then be the inverse. And the reason why that works is because the relationship between a matrix and its inverse is that if I multiplied them together, I should get the identity matrix of the same size. So if I take a matrix and work with it till I get an identity, the idea here is the identity matrix then should become the inverse. So we'll walk through the process here and see how that happens. So first thing I'm going to do is I'm going to augment the matrix with an identity matrix of the same size. So I'm going to rewrite this original matrix as 0, negative 11, 1, 6, but also on the right side of the dashed line I'm going to put the identity matrix that is 2 by 2 or order 2. So then I'm going to use row operations to try and rework the left side to become the identity matrix. So the first thing I'm actually going to do is exchange row 1 and row 2. And the reason I would do that is because I take a look at row 1, I have a 0 in the first spot, and row 2, I have a 1 in the first spot. So if I exchange those rows, it's going to be a little bit closer to looking like our identity matrix there on the left. So it didn't actually operate with any of the rows, just exchange their place. And then the next thing I'm going to do is take row 2 and multiply by negative 1 over 11. And the reason I would do that is because it would make the second entry in row 2 a 1, which is what I wanted. So row 2 is actually finished in terms of operations I have to do to it. It's already 0, 1, and then the right side is, something else. And I don't necessarily need to worry about the right side, because as long as I correctly operate with the left side of the dashed line, the right side should be the inverse. So now taking a look at what I have, I need to somehow make that second entry in row 1 a 0. So the way I'm going to do that is by taking row 1 and subtracting 6 times row 2. So what I should get is 1, 0, 6 over 11, 1. And again, I'm not writing all the work out, but feel free to pause the video and just work that step out and make sure that you get what I got here. And then I'll leave row 2 alone. The idea here is now that I've taken the original matrix I was given and rewrote it as an identity matrix, the matrix I got on the right side of the dashed line should be the inverse of the original. And the way we can verify that is by taking those two matrices, the given one and the inverse I found, and multiplying them, and I should get a 2 by 2 identity matrix. So for example 3, we're going to complete the same process of computing a inverse of a matrix by rewriting this matrix augmented with a 3 by 3 identity matrix. And again, the process will be to use row operations to make the left side an identity matrix, which would then make the right side our inverse. So the first step I would do is take row 2 and add 3 times row 1 to it, and also take row 3 and subtract 2 times row 1. The reason why I'm going to complete both of those steps at the same time is because I'm using row 1 as an operator, not actually changing row 1. So one of those steps doesn't depend on the other. And if you want to write them in 2 separate steps, this is just what I would do. You don't have to do these exact steps, but it will allow me to get a 0 in the first entry of rows 2 and row 3. So row 1 again would be unchanged, so I'm just going to rewrite that. And then what I should get in row 2 should be 0, negative 1, 0, 3, 1, 0. And then what I should get in row 3 should be 0, 1, negative 1, negative 2, 0, 1. And now from here, what I'm going to take a look at is if there's any way for me to get a 0 in row 1 or row 2 in one of my other columns. So if I look at row 2 and row 3, I have a negative 1 in the second entry of row 2 and a positive 1 in the second entry of row 3. So if I added those rows together, that would allow me to rewrite the third row with a 0 in the third column. So my next step, rows 1 and row 2 will be unchanged. So if I added row 2 to row 3, I should get 0, 0, negative 1, and then 1, 1, 1. Now from here, what I see is row 2 and row 3 look very much like an identity, or the second and third row of an identity matrix. The only difference is it's negative 1 there instead of positive 1. So what I would do next is multiply row 2 and row 3 by negative 1. So row 1 I'm going to leave unchanged for now. And then I should get 0, 1, 0, negative 3, negative 1, 0 in row 2, and 0, 0, 1, negative 1, negative 1, negative 1 for row 3. And then in terms of finishing this left side to be an identity matrix, I'm one step away. The way I know that is I have 1, 0, negative 2 in the first row, and I have a 1 in the third entry of row 3. So if I can take row 1 and add 2 times row 3, it should give me 1, 0, 0 in the first row. So provided I complete that process with the right side of the dash line correctly, I should be done with my identity matrix on the left hand side. So again, what I should get is 1, 0, 0, because 2 times 1 is 2, added to negative 2 is 0, and then rows 2 and 3 I will leave unchanged. So what I have here is the left side is now the identity matrix, the right side should now be our inverse. So to answer the question, it says compute the inverse, I would just write the right side of this augmented matrix, and that should be the inverse of my original matrix. Again, the check would be to take this inverse I found, multiply it by the original matrix, and I should get order 3 identity matrix. So for example 4, we are going to compute the inverse by using the same process. So first we should augment this matrix with the 3 by 3 identity matrix, and then use row operations to rewrite the left side of the dashed line as the identity matrix, which should then yield our inverse on the right side. So the first thing that I would do here is I would take row 2 and subtract row 1, and I'm also going to take row 3 and subtract row 1. The reason I chose those operations is because both of those operations would give me a 0 in the first entry of rows 2 and 3. So then row 1 would remain unchanged, and then row 2 would become 0, 6, 13, negative 1, 1, 0. That's again subtracting the values from row 1. And then row 3 should become 0, 5, 11, negative 1, 0, 1. And now looking at what I have, there's a couple ways you could go from here. The one thing I wouldn't do, although it is a viable option, is try and get the coefficients of maybe column 2 or column 3 for the bottom 2 rows to match up. The reason I wouldn't do that is because then I'd either have to make them both 30 or make them both like 143, which although it is viable, you end up making the arithmetic a little bit more difficult, especially if you're having to work without a calculator. So what I'm actually going to do is take row 2 and subtract row 3. And the reason I would do that is because it's actually going to give me a 1 in the second entry of row 1. Again, it's not going to make a 0 here, but that's okay because it will give me something that'll be a little bit easier to operate with. So if I take row 3 away from row 2, I should get 0, 1, 2, 0, 1, negative 1 for row 2. And then looking at what I have now, I can use the 1 in the second entry of row 2 to operate with the third row, try and make that second entry a 0 in row 3, and possibly in the first row as well. So I'm actually going to try and complete 2 steps here. So I'm going to take row 3 and subtract 5 times row 2, and then I'm going to take row 1 and add 4 times row 2. So if I do that, my first row would become 1, 0, 0, 1, 4, negative 4, which works out nicely that both the second and third entries in row 1 became zeros. I was really only trying to make the second entry a 0, which it was coincidence that the third entry also became 0. And then row 2 would remain unchanged for now, and then the third row should become 0, 0, 1, negative 1, negative 5, 6. So at this point, the only row that needs to be operated on is the second row, and I need to make that third entry in the second row a 0. So I'm going to do that by taking row 2 and subtracting 2 times row 3 from it. So if I do that, again, keep my first row and my third row the same. And the second row should give me 0, 1, 0, and then 2, 11, negative 13. So what I have here is an identity matrix of order 3 on the left side of the dash line, and the right side should be the inverse matrix of the original one that was given to me in this problem. To verify that, again, you can multiply our answer here times our original matrix, and we should get the identity. That's one way you can check to make sure that you computed this correctly. So for the next few examples, we're going to use matrix algebra to solve equations, and it's going to incorporate the idea of the inverse. So One thing I want to consider is if you look at example 5, we have the equation ax equals b. And what that is a is a matrix, x is a matrix, and b is a matrix, and we want to solve for x. But x isn't just a single variable, it's actually a matrix of variables. So instead of just dividing both sides by a, we can use the fact that if I multiplied both sides of the equation by a inverse times a is an identity matrix. So an identity matrix times x should just give me x on the left side, and I can compute x, or find the values of that matrix by multiplying a inverse times b. So the first thing we're going to do for example 5 is that we are going to rewrite the equation as x equals a inverse times b. And to complete this multiplication, we have a inverse is given and b is given, so we can multiply those. But in terms of the size of x should be a 2 by 1 matrix because both a inverse and b have 2 rows, so that dictates the size of our variable matrix. And then we're going to complete the operation on the right side of the equation, and what we should get then is a value for x and y. So before we actually complete the operation, we should check that the operation is defined. So we have a 2 by 2 matrix for a inverse, and we have a 2 by 1 matrix for b. So the number of columns in a inverse and the number of rows in b is the same, so therefore this operation is defined, and the size of the new matrix should be a 2 by 1. So to complete the operation, we would just multiply row 1 times the column and row 2 times the column, so negative 9 times 30 plus 7 times 39, and negative 4 times 30 plus 3 times 39. So then I can say xy is going to be equal to 3 and negative 3, so therefore x is 3 and y is negative 3. For example 6, we're going to complete the same process, except we're going to have a inverse times c. That's how we can rewrite that equation. And again, x is going to be a 2 by 1 matrix based on the sizes of a inverse and c. And then again, check if this operation is defined. It will be based on the same reasoning as the previous example, but it is a good habit to check. So a 2 by 2 times a 2 by 1, the operation is defined, and the size should be a 2 by 1. So it would be the first row times that column of c, and then the second row times the column of c. And then to actually find the values of x and y, we should complete the operations there. So negative 9 times negative 45 plus 7 times negative 71 should give me negative 92. And then negative 4 times negative 45 plus 3 times negative 71 should give me negative 33 for y. So we can just say x is negative 92 and y is negative 33. And for the last example, we are going to compute or solve for x, and we're going to rewrite this equation as x is going to equal d inverse times e. And then again, in terms of the size of x, in this case, x is going to be actually a 3 by 1 matrix because d inverse and e both have 3 rows. So I'm going to write d inverse and write e. So to solve for x, y, and z, I would just compute this multiplication. First we should check that the operation is defined. So we have a 3 by 3 multiplied by 3 by 1. So the operation is defined, and the size of the new matrix should be a 3 by 1. So I'm going to rewrite the variable matrix x, y, z, and then write my operation. So row 1 times that column is negative 1 times 28 plus 2 times 9 plus negative 2 times 22. And then row 2 times the column of e is negative 1 times 28 plus 3 times 9 plus 0 times 22. And the third row times the column is written there. And then to find the values of x, y, and z, we just have to complete the operations here. So x, y, z is going to give me, so for the first entry I should get 2, second entry I should get negative 1, and the third entry I should get 4. So we can say the value of x is 2, the value of y is negative 1, and the value of z is 4. So what we're finding here is the column matrix x, y, z, that if I multiplied it by matrix D, I should get the matrix E. And we're doing that by using the fact that the inverse was given to us. First of all, we know D inverse, but D inverse times E gives me my variable matrix. And then obviously to check, if I took the matrix I just found, 2, -1, 4, and multiplied it by matrix D, I should get matrix E.